Hi, I'm Jonathan Aldrich. Today, let's talk about subroutines and control abstraction. Control abstractions provide different ways of organizing program operations. Perhaps the most familiar is a subroutine, which performs some operation for a caller and usually accepts parameters and often returns a result. Subroutines that return a result are called functions, whereas subroutines that don't are often called procedures. Some other control abstractions include exceptions. An exception exits a context without returning so that an error that occurred within that context can be handled somewhere in the surrounding context. A coroutine allows a program to switch between two or more execution contexts. Finally, asynchronous programming responds to events in the environment, and in particular, organizes the response to sequence of events via straight-line code while allowing the system to do background work between the events as they occur. Now, everyone is familiar with subroutine abstractions, but let's consider how they're implemented. What is the calling sequence of instructions used to call a subroutine, and how does that subroutine get set up and torn down? Let's start with a review of what a stack frame looks like. Recall that there are several different allocation strategies. We can keep data statically for global variables, or we can put it on the stack if it lives the length of a function, or we can allocate it on the heap. Zooming in on the stack, let's look at the contents of a stack frame of a function. Here we have a diagram back from chapter 3, where we have a bunch of subroutines organized in a stack. So subroutine A starts executing, and then it calls subroutine B, which calls itself recursively. So we have a stack with A and then B and then B. And then maybe B calls subroutine C, and subroutine C calls subroutine D, which is the current one executing. If we zoom in on one piece, we'll see what goes on in one of those stack frames, in this case, the stack frame for subroutine C. We have some bookkeeping. There's the return address, which tells us how to get back to the caller. We have some saved registers, we have a static link, and maybe some other information. The stack frame will also contain the arguments to the current procedure and to procedures that we call, and also the return values that either we are going to return ourselves or that we get from functions that we call. There'll also be local variables that we need to use within the routine, and perhaps some temporaries to store data in transit during computation. How do we maintain the stack frame? Well, the stack frame is maintained and created by, first of all, a sequence of instructions that is used to call the function. So that sequence will be in whatever is calling us, the caller. And then in our function, we will define a prologue that sets things up and an epilogue that tears things down. Now, there's a little bit of a trade-off between doing things in the calling sequence and the caller versus the prologue and the epilogue of the callee. In general, we can save code space by doing as much work in the callee as possible, because that work will be reused across all calls to the callee. On the other hand, we might save execution time by doing some work in the caller instead. For example, the caller has some context. The caller knows which registers are in use at the call and which ones are not. We need to save the ones that are in use, but we don't need to save the others. In general, a common strategy is to divide registers into two categories: those that are saved by the callee, called callee saves, and those that are saved by the caller, called caller saves. For the callee saves registers, we typically want to use variables and other long-lived data. So this data will live across multiple calls, and if we're calling another function, then it will save them for us so that we can get them back when we're done. On the other hand, caller saves registers are often used for transient values, values that we may not need to use across calls. The callee will not save these for us, and so as the caller, we only need to save them if we're going to use them again. And so if they're transient values, then hopefully no one needs to save them, right? Neither the callee nor the caller has to save the registers. Let's look at setting up the stack frame in more detail. We start with the calling function. The caller will, first of all, saves the caller saves registers. But it only needs to save the ones, as I mentioned, that are needed after the call. Otherwise, we can save the work. It then computes the arguments and moves those arguments to the stack in the place that is reserved for them. Typically, at the top of the caller's stack frame, just before we get to the callee stack frame, that's where we'll put the arguments to the caller, to the callee. In some cases, we'll pass the values in a register instead of on the stack. If we're in a language that has nested subroutines, the caller will also compute the static lick and pass that as an argument. Finally, it will use a special call instruction for invoking the subroutine. This jumps to the beginning of the subroutine, but it also passes the return address either on the stack or in the register. Now let's look at the callee. The callee's prologue is the sequence of instructions at the very beginning of the callee. This will allocate a frame by subtracting from the stack pointer. We'll save the old frame pointer to the stack and then update the frame pointer to point to the frame so that we can then access the elements of the frame after this. Finally, we'll save all the callee saves registers, but we only need to save them if they might be overridden, either by our code or by the code of functions that we call. And so again, if we know that some of these callee saves registers won't be used by us, then we don't have to do the work of saving them. We then run the function, and at the end of the function, there's an epilogue. This epilogue will move the return value, if there is a return value, into a register or into the space dedicated for it in the stack. We'll restore any of the callee saves registers that we used, and then we'll restore the stack and the frame pointers to what they were before the call. Finally, that gets us to the place where we can jump back to the return address. Finally, in the caller, we'll move the return value to wherever it's needed, and we'll restore our own caller saves registers, again, if we need the values they held before the call. Now, all of that can be a fair amount of work, and so modern compilers try to optimize the stack maintenance code to reduce the cost both in code size and in execution time. Once upon a time, there were a lot of special instructions that had to do with calls and returns. For example, the x86 architecture has enter and leave instructions that manipulate the frame pointer. Today, we mostly avoid those special instructions. The only one we really use is the call or JSR instruction, because that does a jump, but it also sets the return value onto the stack or a register so we know where to get back. Typically, modern compilers will pass arguments in registers because it's faster. The callee will usually have to use those right away, and they'll use them from the registers, and so they're right there where needed. Typically, we will also reserve some space for those arguments on the stack so that the callee can put them there if it needs to. Modern compilers typically skip the frame pointer. We don't really need a frame pointer. We can just access everything off of the stack pointer as long as the stack frame is of known constant size. We just compute where to go from the stack pointer, and we're good to go. Finally, if we have a very simple leaf routine, it may just take the arguments in registers, return a result in register, and do all the computation in registers. In this case, who needs the stack? We can avoid using memory at all, and then we can get rid of almost all of the prologue and the epilogue. Let's take a dive and look at the x86 calling convention, which tells us a little bit about how this calling sequence might be implemented on these processors. The System V AMD64 ABI is the de facto standard on Unix for Intel-based machines. So if you have an Intel-based Linux machine or an Intel-based Mac, they'll be using this calling convention. In this setting, the callee saved registers are, by convention, the stack pointer RSP, as well as RBP, RBX, and R12 through R15. The x86 architecture is a long legacy, and so these names have, are irregular, kind of reflecting that history. RSP is our stack pointer. It points to the end of the last allocated stack frame. RBP was originally intended as a frame pointer, but modern compilers, as I mentioned, usually don't use frame pointers. And so RBP can just be used as any old register. However, we do need to do a callee save on it, just as we would do a callee save if it were actually the frame pointer. Finally, the first 6 64-bit arguments are passed in registers. The first argument will be passed in RDI, and then in sequence, we'll pass the second argument in RSI, then RDX, then RCX, then R8, then R9. Any additional arguments are passed on the stack, and we do that in reverse or right to left order. If arguments are too big for a register, then we'll also pass them on the stack. If we have a result, if it can be stored in 64 bits, we'll return it in the register RAX. If the return value is larger, then what we'll do is we'll allocate some space on the stack for it before making the call, And then the address of that space allocated on the stack will be passed in RDI as a hidden first argument. Remember, RDI is where we pass the first argument of the function anyway. An alternative to calling sequences and making function calls in general is inlining. The idea of inlining is we expand the definition of a function inline into the caller. We just paste all the code into the caller and then generate assembly as usual. Now, we can only do this under certain conditions. We have to know what the callee is. It has to be statically known, so we can't be doing dynamic dispatch or calls through function pointers unless we somehow analyze that so we know exactly what the function pointer is going to be. Generally, we want the callee to be short because otherwise we're copying a lot of code into the caller, and if we do that for multiple callers, we're going to blow up our code size. But if we have short functions, that's okay. And of course, if a function is called only once and we know that, then again, we're not really wasting any space. What inlining does is it enables a lot of valuable operations. First and foremost, it eliminates the entire calling sequence prologue and epilogue. But besides that, it allows the compiler to optimize the caller and the callee code together, knowing what's in the, when we optimize the caller code, we know what's in the callee code, and when we optimize the callee code, we know what's in the caller, and so we can do constant propagation and loop fusion and all sorts of different things. C and C++ actually have an inline keyword that hints that this is a short function that should be inlined. Programmers like to use this hint sometimes, but in practice, compilers can really do what they want. And actually, that's usually the best thing because what we've seen is that often compilers make better decisions about inlining than programmers do. Trust your compiler. Let's check our understanding of calling sequences.